blockchain structure is an ordered, back-linked list of blocks of transaction. The blockchain can be stored as a flat file or in a simple database. The Bitcoin Core client stores the blockchain metadata using Google's LevelDB database. Blocks are linked back, each referring to the previous block in the chain. The blockchain is often visualized as a vertical stack with blocks layered on top of each other and the first block serving as the foundation of the stack. The visualization of blocks stacked on top of each other results in the use of the terms such as height to refer to the distance from the first block and top or tip to refer to the most recently added block. Each block within the blockchain is identified by a hash generated using the SHA-256 cryptographic hash algorithm on the header of the block. Each block also references a previous block known as a parent block through the previous block hash field in the block header. In other words, each block contains the hash of its parent inside its own header. The sequence of hashes linking each block to its parent creates a chain going all the way back to the first block ever created, known as the Genesis block. Although a block has just one parent, it can temporarily have multiple children. Each of the children refers to each of the children refers to the same block as its parents and contains the same parent hash in the previous block hash field. Multiple children arise during a blockchain fork, a temporary situation that occurs when different blocks are discovered almost simultaneously by different miners. Eventually, only one child block becomes part of the blockchain and the fork is resolved. Even though a block may have more than one child, each block can have only one parent. This is because a block has one single previous block hash field referencing its single parent. The previous block hash field is inside the block header and thereby affects the current block's hash. The child's own identity changes if the parent's identity changes. When the parent is modified in any way, the parent's hash changes. The parent's changed hash necessitates a change in the previous block hash pointer of the child. This in turn causes the child's hash to change, which requires a change in the pointer of the grandchild, which in turn changes the grandchild, and so on. This cascade effect ensures that once a block has many generations following it, it cannot be changed without forcing a recalculation of all subsequent blocks, because such a recalculation would require enormous computation and therefore energy consumption. The existence of a long chain of blocks makes the blockchain's deep history immutable, which is a key feature of Bitcoin's security. One way to think about the blockchain is like layers in a geological formation or glacier core sample. The surface layers might change with the seasons or even be blown away before they have time to settle, but once you got a few inches deep, geological layers become more and more stable. By the time you look a few hundred feet down, you are looking at a snapshot of the past that might have remained undisturbed for millions of years. In the blockchain, the most recent few blocks might be revised if there is a chain calculation due to a fork. The top 6 blocks are like a few inches of topsoil, but once you go more deeply into the blockchain beyond 6 blocks, blocks are less and less likely to change. After 100 blocks, there is so much stability that the Coinbase transaction, the transaction containing new mined Bitcoin, can be spent a few thousand blocks back a month, and the blockchain is settled history for all practical purposes. While the protocol always allows a chain to be undone by a longer chain, and while the possibility of any block being reversed always exists, the probability of such an event decreases as time passes until it becomes infinitesimal. Structure of a block. A block is a container data structure that aggregates transactions for inclusions in the public ledger, the blockchain. The block is made of a header containing metadata, followed by a long list of transactions that make up the bulk of its size. The bulk header is 80 bytes, whereas the average transaction is at least 250 bytes, and the average block contains more than 500 transactions. A complete block with all transactions is therefore 1000 times larger than the block header. Table 9.1 describes the structure of a block. At 4 bytes, block 1, the size of the block in bytes following the field, 80 bytes block header. Several fields from the block header, 9 bytes variant. Transaction center, how many transactions follow. Variable transaction, the transactions recorded in this block. Block header. The block header consists of 3 sets of block metadata. First, there is a reference to a previous block hash, which connects this block to the previous block in the blockchain. The second set of metadata, namely the difficult timestamp and nonce, relate to the mining competition as detailed in chapter 10. The third piece of metadata is the Merkle tree root, a data structure used to efficiently summarize all transactions in the block. Table 9.2 describes the transaction of a block header. Block identifiers. Block header, hash, and block height. The primary identifier of a block is its cryptographic hash, a digital fingerprint made by hashing the block header twice through the SHA-256 algorithm. The resulting 32-byte hash is called the block hash, but is more accurately the block header hash, because the only block header is used to compute, for example. So I'm not going to read all this. Is the block hash of the first Bitcoin ever created. The block hash identifies a block uniquely and unambiguously, and can be independently derived by any node by simply hashing the block header. Note that the block hash is not actually included inside the block's data structure, neither when the block is transmitted on the network nor when it is stored on a node's persistent storage as part of the blockchain. Instead, the block hash is computed by each node as the block is received from the network. The block hash might be stored in a separate database table as part of the blockchain, as part of the block's metadata, to facilitate indexing and faster retrieval of blocks from disk. A second way to identify a block is by its position in the blockchain, called the block height. The first block ever created is at block height 0 and is the same block that was previously referenced by the following block hash. A block can thus be identified two ways: by referencing a block hash or by referencing the block height. Each subsequent block added on top of that first block in one position higher in the blockchain, like boxes stacked one on top of the other. The block height of January 1st, 2017 was approximately 446,000, meaning that there were 446,000 blocks stacked on top of a first block created in January 2009. Unlike the block hash, the block height is not a unique identifier, although a single block will always have a specific and invariant block height. The reverse is not true. The block height does not always identify a single block. Two or more blocks might have the same block height competing for the same position in the blockchain. The block height is also not part of the block data structure. It is not stored within the block. Each node dynamically identifies a block's position height in the blockchain when it is received from the Bitcoin network. The block height might also be stored as metadata in an index database table for faster retrieval. The Genesis block. The first block in the blockchain is called Genesis block and was created in 2009. It is the common ancestor of all blocks in the blockchain, meaning that if you start at any block and follow the chain backward in time, you will eventually arrive at the Genesis block. Every node always starts with a blockchain of at least one block because the Genesis block is statically encoded within the Bitcoin client software such that it cannot be altered. Every node always knows the Genesis block's hash and structure, the fixed time it was created, and even the single transaction within. Thus, every node has the starting point for the blockchain, a secure route from which to build a trusted blockchain. See the statically encoded Genesis block inside the Bitcoin core client in chainparams.cpp. The following identifier hash belongs to the Genesis block, so I'm not going to read all this. You can search for that block hash in any Explorer website such as blockchain.info, and you will find the page describing the contents of this book with the URL containing that hash. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.